What we want to do today is we want to take a systems approach to understanding the system of blueberries and cardiovascular health. We're going to begin with understanding the truth about the cardiovascular system. Then we're going to talk about blueberries, their biological functions and health benefits. What gets in the way of getting this knowledge out there is that there's an attack on freedom to talk about these things in a much more global way. Most of the discourse is really about the singular big pharma solution. There's also constraints on medical doctors. Medical doctors are frankly constrained to even speak about a nutrition and diet, and it's because of their whole educational process. Irrespective of those problems, we're going to talk about the possibilities of blueberries on cardiovascular health. We're going to look at the molecular mechanisms of action. Exactly, we're going to look at how components in blueberries assist the cardiovascular system, so you understand the why you're seeing those positive things in the media from some of those health posts and journals, the clinical evidence, how much you should take, and the sourcing where you should get your blueberries. Okay, so let's talk about the cardiovascular system. Again, for those of you who know it, this will be a review, but fundamentally, this is a system, right? A system is not just any one thing. A system is composed of a set of parts. In our course, Foundations of Systems, we really educate everyone on this. But first of all, the cardiovascular system is composed of three components: the heart. And by the way, sometimes it's good to take notes because you'll know it a little bit better or visualize. You have the heart, you have the blood vessels. We'll talk about what those are. Multiple systems are in that, right? And then you have the blood that flows through those blood vessels that's pumped by the heart. And the blood is also itself a system. It's composed of not just red blood cells, but which carry the oxygen, but it also includes the white blood cells, which support your immune system. So it's a complex system of systems. The cardiovascular system is not just one thing. And if you look at a very detailed level at the vessels, what you will see is that the vessels consist of three subsystems: arteries, veins, and capillaries. Now, if you look over here, the arteries are the things that carry blood to the heart, okay? So that's the red. So the blood gets oxygenated blood, comes from the lungs, goes through the left atrium, and then it gets sent down to your left atrium. It gets sent to your left ventricle, which then pumps it out to the rest of your body. And then as your body uses it, gets deoxygenated, comes back through your right atrium, and then it goes up through your right ventricle or down into your right ventricle, and then it gets pumped back into your lungs where the deoxygenated blood gets oxygenated and the cycle repeats, okay? The important thing to understand is the arteries are the large blood vessels that carry oxygenated blood. So arteries, oxygenated, arteries, oxygenated. Your aorta, for example, being one of the biggest arteries, which pumps all that oxygenated blood. The veins are the large blood vessel that carry the deoxygenated blood to the heart. So arteries carry blood away from the heart, veins bring blood, deoxygenated blood. Now the capillaries are the very, very fine blood vessels that deliver the nutrients and oxygen to the tissues and cells, and they're all throughout your entire system. And you can see it in many ways like the roots of a tree, right? You can see all the different ways that they separate here. For those of you just listening to the audio, you have the arteries coming in, the blood goes in, oxygenated, and then the capillaries are the fine blood vessels, and then the capillaries then go to venules, which go back to the veins. So there we go. Now, if we get even closer, let's look at the structure of all of this vasculature, this piping. And the reason I want you to understand this, remember, we're not just here to tell you what to think, but we're here to tell you why this stuff works. In order to understand the why of the cardiovascular system, we have to understand the physical mechanics of what are these structures made of. So what is that vasculature, cardiovascular system? What is that vasculature made of? And what you notice here is the vasculature of be it the arteries or the capillaries or the veins, are composed of one or more of these structures. And there's three structures: the adventitia, the tunica media, or the tunic intima. The adventitia is the outer layer, okay, which out of the, let's say, the veins or the arteries, which provides, and by the way, capillaries don't have the adventitia, they only have the tunic intima, but the veins and the arteries have all three layers. They have the outer layer, which really gives structural support. And in the case of the tunica media, that's the middle layer that's composed of the elastic and musculature tissue, which regulates the internal diameter of the vessels. And you can see in the case of the artery, that middle layer is much thicker, okay, versus the veins where the adventitia is thinner, okay? And then the tunica intima is the inner layer of the arteries and the veins, which consists of the endothelial cells. And that provides a frictionless pathway for the movement of blood. So the endothelial is the cells which cover the inside of the arteries, inside of the veins. And when it comes to the capillaries, that's all the capillaries are composed of. The capillaries are only composed of the endothelial. So think about what I'm saying. When you look at the entire vasculature in your entire body, okay, everywhere, all that blood blood that's flowing through you, most of it is the capillaries, which are just composed of these cells called the endothelial cells. So think about that. So if you want to have good vascular function, those endothelial are extremely important, the endothelial cells. And the way you want to visualize the endothelial cells is if you think about you have a floor in your kitchen or your bathroom and you have the tiles on the floor. Those individual tiles are equivalent to the endothelial cells, which form the tile framework of your capillaries, right? Which are those fine vessels that's in this diagram here, all those capillaries. So in order to have really good cardiovascular function, if you want to look at it from a purely structural standpoint, you want to think about those endothelial cells need to be in good shape. So that's a big takeaway. So the question is, what supports endothelial function? Because these cells are all throughout your body. The better endothelial function you can have, because that's the part that's interconnected that composes your whole cardiovascular system, you're probably going to have better cardiovascular health. So that's what we want to talk about. So that's the takeaway, right? So think about it very practically. It's that system that is your vasculature is composed of. Now, to study this, we use a very powerful technology that I built out of my research work at MIT called Cytosol. And Cytosol is a technology that I initially built because I recognized the entire pharmaceutical development model was archaic. The way they build pharmaceuticals is you have to understand a pharmaceutical is a single compound, chemical that doesn't occur in nature. That's what a pharmaceutical is. It's a single molecule compound. Sometimes they'll combine some of those molecules called cocktails, but most of the time it's a single compound. And in order to discover a drug, they'll play around with a single synthetic compound. They'll put cancer cells, let's say if you're looking for cancer, in a test tube, they'll throw a compound in there and say, oh, does it do anything? Nope, it doesn't. They'll test another compound. Oh, it's doing something in a test tube. That's called in vitro testing or screening. If that's positive, then they'll go kill a bunch of animals. That's called in vivo testing, animal testing. And then if all of that, you don't kill too many animals and they think the compound works, and you go into phase 1, phase 2, phase 3 clinical trials, the FDA has to approve that. That is a pharmaceutical development process. It's a very expensive process, about up to $5 billion, 13 years. And the stuff that comes out of it may cause all sorts of side effects. So when I looked at this whole process, I said, this is really archaic. We build airplanes by not just throwing test pilots in, we use a computer. So that led to really the development of Cytosol. Now, the current pharmaceutical model is falling apart. You can see they spend a lot of money on R&D and they're finding less and less new molecules. This is why the pharmaceutical industry needed vaccines. Vaccines were their way out of this business fiasco. And if you look at the pharmaceutical companies like Pfizer, and I've talked about this in other videos, they were tanking. They were bleeding money. And just in the past year, Pfizer made $40 billion more than their revenue from the previous year. They made $80 billion total. But in the last 10 years, Pfizer had lost $25 billion. So vaccines were what really saved the day. And you got to understand that pharmaceutical companies have been failing based on their drug model. So when we, wanted to look at Cytosol really helps us look at all the research that's out there, organize that research as you're seeing here. So right now there's over 2,970 research articles done on blueberries and 103 clinical trials over the last 110 years. And when you look at this research, what is a blueberry? You're going to find out a blueberry is not a synthetic compound. A blueberry is composed of many, many different chemicals. So what does that mean? Pharmaceutical companies do not have the wherewithal to actually study food. They can only study a single compound, okay? They can't study a blueberry. They don't have the tools. Cytosol provides us the tools to do that because a blueberry is a multi-combination therapeutic. It's got many, many different compounds. So that's what the revolution with Cytosol is. We can actually validate food and combinations of many, many compounds. So you can see people have done a lot of clinical trials. Clinical trial is not a systems approach. It's good. So they put something into someone's body and they look at what the output is. But the good news, a lot of clinical work has been done. The work of Cytosol really helps figure out why this stuff works. And Cytosol literally takes all the research, all that work that's been done. We extract out the molecular mechanisms. We understand the pathways relative to cardiovascular health. And then we organize that data, which is what I'm presenting to you today. So when we look at the Cytosols approach, what we want you to understand is what is the endothelial, those tiles that make up the surface of the capillaries and the arteries and the veins that are all throughout you, and what actually supports endothelial function. Because if you can figure out and know for yourself, hey, this is this is why this is the difference between a healthy cardiovascular system and a non-healthy cardiovascular system. Now you can think for yourselves and you guys can make decisions. So I'm just here to give you the systems analysis based on the science today. But you're going to very quickly understand the role of nitric oxide on endothelial function, okay? So let's just jump into that. And this was work that I was a part of with some other great researchers at MIT, Brigham and Women, Harvard Medical School, and King's College in London. And what we were looking at was a very important molecule called nitric oxide, which occurs naturally in your body. Nitric oxide is a vasodilator, which means it relaxes your blood vessels. It's very important maintaining blood pressure. It's anti-arthrogenic, which means against arteriosclerosis. It is generated, so nitric oxide gets generated when this chemical eNOS, which means endothelial nitric oxide synthase, when this helps convert, that's what catalysis means, or create or support the creation of L-arginine, okay? So when nitric oxide helps catalyze L-arginine into nitric oxide, so eNOS catalysis of L-arginine creates nitric oxide, you're going to see how that happens. And one of the ways it happens is when you exercise, when your body moves blood and the blood flow creates shear stress that triggers nitric oxide. So what do we mean by that? To keep it again simple, we want to make this accessible. Here's, let's say, your capillary or your artery, and there's blood flow. You're exercising, you're running, you're exercising, you're doing a good walk, and you're getting blood flow. This blood flow flows over your endothelial cells, and the physical flow, you're going to see why, the results in nitric oxide production. Well, how does that happen? Well, when blood flows, endothelial nitric oxide synthase, eNOS, converts L-arginine, which is an amino acid which you get in your food, to nitric oxide as well as L-citrulline. So again, to put this simply, you exercise, you walk, blood starts flowing through your veins and your arteries, right? Your capillaries. The flow of the blood results in nitric oxide release, but that cannot occur unless you have L-arginine, which means diet is important, right? You have to have L-arginine in your body. Your body is a producer, you get it from the diet. And in the presence of L-arginine, eNOS, which is endothelial nitric oxide synthase, converts that arginine to nitric oxide, okay? And by the way, that nitric oxide was really the basis of the creation of the drug Viagra. Okay, but that's what's going on here. Okay, so it's a complex system here, but what you've just learned is exercise, food, L-arginine results in vasodilation. So it's not just the food, L-arginine, it's not just the exercise. You got to have both here. You got to have enough eNOS to generate nitric oxide. So that's really the takeaway. Complex system. Okay, great. All right. So now how does this work, right? So why does this all work? So now let's put the microscope all the way down. We're looking at one of those endothelial cells. That's what is on the right side here. And what you find is at the molecular systems level, what you see is the surface of the endothelial has a little Christmas tree-like structure right here. I'm pointing to right here. Let me move this right here. And what this does is this Christmas tree structure is known as a glycocalyx. When blood flows, that's what these blue lines represent. The blood flows and it starts shaking this Christmas tree, the glycocalyx. That movement results in the release of nitric oxide. But how does that occur? It occurs through a series of chemical reactions you're seeing here. This is called a molecular pathway. This is a molecular system, okay? So blood flows over the endothelial, it moves the glycocalyx, and the mechanical movement of the glycocalyx initiates the conversion of L-arginine to nitric oxide in the presence of eNOS. Now, how did we find all this out, and were we able to really model? And by the way, someone's saying, good morning from the Philippines. Great to have you. Good to have you. So how does all this occur? Well, using Cytosol, when we looked at all the research that's out there, you find out researchers all over the world have found pieces of these molecular reactions. I mean, no one researcher could discover all of this. So some guys talk about these molecular pathways of calcium influx or eNOS expression or phosphorylation or NO production. You see, each one of these little diagrams is coming from the work of a lot of hardworking scientists all over the world. What Cytosol does is find all those pieces and like a jigsaw puzzle, put it together, and then we can mathematically model it to predict how much eNOS RNA concentration occurs in your blood, in those arteries and capillaries. And this is a mathematical prediction using Cytosol. That's what we're doing. And so over time, Cytosol's mathematical engine, our technology is predicting how much eNOS will get released by literally integrating the research of thousands of researchers all over the world. So what we're doing is, without killing animals, we're taking previous work, organizing it, and mathematically modeling it. Now, the question many people say is, well, this is all good. Is Cytosol real? Well, how do we know that what you're predicting is what actually occurs? So when we did the work with Harvard and MIT and Brigham and King's College, we actually had another researcher, Andrew Koo, who actually went and did the biological experiments, and this is the data from the wet lab. So you notice how beautifully our predictions match what they saw in the lab. So this shows that Cytosol's results aren't just garbage in, garbage out. They actually match, okay? And same here, when we looked at the protein concentration, we match. This was a very important piece of research because for various reasons, I'm able to share this with you. You now understand the complexity of the endothelial, that we can model it, but more importantly, this actually showed that Cytosol can predictively model complex things. And this was published in one of the leading journals in the world, Cell's Biophysical Journal. I was one of the authors with some great people in here from MIT and Harvard. So anyway, want to let you know that we've shown the validity of Cytosol, but more importantly, the mechanisms, okay? Someone said they're from, yes, it's really cool. Someone says this is cool. Yes, it's very cool, Christine, because we are able to use the computer to model very complex functions that pharmaceutical companies cannot do, okay? Now, using this, as I mentioned, we started the Cytosol Open Science Institute. I recommend you guys go there. You can support the research. Eventually, we're going to be spinning these entities off into companies. And for those of you wanting not only to support it, but own a piece of these companies, we're going to make that accessible. So keep an eye out for that. And when you support our work, you actually get access to the Foundations of Systems course. You can use it. So there's a reciprocity here. And please, I can't overemphasize, please take the Foundation of Systems course. You support our work, you support yourself, and get the book. Okay. Now you understand the complexity of the cardiovascular system. You've really learned what is the endothelial, that it's really important if your endothelial is working well, the glycocalyx works well, your body releases nitric oxide, etc. Okay. So now, what is the truth behind a blueberry, right? Let's look at the science of a blueberry. You understand the system. The blueberry itself is a system. It's not just any one thing. It's got macronutrients, fiber, protein, fat, 2 grams of fiber per 100 grams of blueberries, 0.7 grams of protein and fat. So notice it's got fiber, protein, and fat. Okay. We have a lot of micronutrients. These are the macronutrients, micronutrients, vitamins, mineral, phenolic compounds, and anthocyanins. Okay. Let us also recognize the vitamins are vitamin K, vitamin C, phosphorus, potassium, and beta carotene. A lot of beta carotene in blueberries. But there are some major phenolic compounds, and these are the ones that really have the active effects on the cardiovascular system. The coumaric acid, the pelargonidin 3-glucoside, the fisetin, the catechin, the quercetin, and the cinchonine. Okay, so these are some of the major phenolic compounds. These are like, think about, these are like the quote unquote, the real medicine. They're the quote unquote drugs, but they come in combination, but they're naturally occurring in nature. Okay, so these are the organic chemical structures of these. You can see the anthocyanins, the proanthocyanin A, proanthocyanin B, the quercetin, and the ellagic acid. Okay, so let's look at the biological effects of blueberries. Well, first of all, blueberries are anti-inflammatory, antioxidant, anti-diabetic, anti-cancer, hepatoprotective. They protect your liver, anti-obesity. Okay, so next time you go down the produce aisle, it probably is very valuable for you to pick up this medicine. Blueberries are a medicine. Okay, a lot of very powerful effects. So what are the health benefits? Well, they protect cardiovascular disease, alleviate hypertension, liver health, vision health. A lot of research done on blueberries and vision health, diabetes, obesity, cognitive function, and cancer. Today, we're focused on the cardiovascular aspect. And what I want to share with you is when you look at all of these compounds with Cytosol, we're able to understand this. And some of you may know that someone just said, hey, have you used Cytosol for your guys' self? We have, because for years, for the last nearly 15 years, many companies use Cytosol to really figure out which combination of nutrients worked. More recently, we said, hey, why don't we use Cytosol to really go after many of the health ailments? So what we did was we looked at the area of pain and inflammation, and we modeled all those molecular pathways, and we looked at all the potential compounds in nature, and we came up with a very specific combination, MV25, which leveraged Cytosol, but it was our own research, meaning we we've done a lot of research at many companies, but this was our own discovery. And let me show you what MV25 is, and you also understand how Cytosol works. But more importantly, that with this capability, we're actually able to understand food as medicine.